Hi guys, there's some missing minutes in chapter 3, part 1. So let's get those missing minutes. Let's start out. We were talking about shielding and the fact that inner electrons shield outer electrons. Even electrons in the same shell can give a little bit of interference. And we were talking about penetration and how penetration affects the amount of shielding. Okay, now I'm going to scroll down here. Here we see 1s, 2s, and 2p. What I want you to notice on this graph is that 2s has more penetration than 2p. So therefore, more penetration, a stronger interaction with the nucleus. Okay? If we go out even further, and we look here at 3s, 3p, and 3d, I want you to notice that 3s has more penetration than 3p, then has more penetration than 3d. Okay? So this means that 3s, 3p, and 3d in a multi-electron multi-electron atom are going to have different energies, just like the 2s and the 2p in a multi-electron atom are going to have different energies. Okay? So this means that subshells in the same shell for a multi-electron atom have different energies. The s orbital in a subshell is always going to be lower in energy than a p, which is going to be lower in energy than a d, which is going to be lower in energy than an f. We don't worry about any orbitals greater than f because we don't see them in a ground state atom. Remember, a ground state atom is an atom that has all of its electrons in the lowest energy positions available. Now let's compare the energies of orbitals, okay, in between shells. Okay guys, now these are some images that I've taken out of books. Okay, get this blown up as big as possible. What I want you to see is that 1s is always lowest in energy, and then 2s and then 2p, 3s, 3p. Now I want you to notice that 4s, okay, is lower in energy than 3d. So 4s is going to get electrons before 3d does. And then 4p, and then 5s, and 3d. Now this is kind of a clunky drawing. We're going to use this one. Okay? In this drawing, we kind of follow the arrows. 1s is always the lowest in energy, and in an electron configuration, 1s is always the first position to get electrons. Then 2s, then 2p, then 3s, then 3p, 4s, and you just keep following the arrows. Now let's scroll. Okay, now this is a chart that you can do fairly quickly on a piece of paper. Just write out 1s and the next line 2s, 2p, and the next line 3s, 3p, 3d, so on and so forth, and then draw your arrows in. Okay? All right. Now, this brings us to electron configurations. Electron configuration is a listing, okay? It's a listing of all the electrons in an atom or monoatomic ion, charged particles, in this case a charged atom, for the ground state of the atom. Ground state is when all the electrons in the atom are in their lowest energy position available. And to do an electron configuration, we use the Aufbau principle. Aufbau in German means to fill up. So the Aufbau principle says that in ground state, okay, atoms or ions, electron configurations with the lowest energy is the one that fills in electrons from lowest energy position orbital in the atoms outward to higher energy positions. So if we start doing sets of quantum numbers for elements on the periodic table, beginning with hydrogen, and we move to the next one, we're essentially just moving or adding one more electron in as we move. to the next highest energy position available. Or if an orbital is, no, and to the, okay, Aufbau says we feel essentially from the bottom up and we just move to the next energy position available as we move on. Each electron in an atom is going to have its own unique set of 4 quantum numbers. Okay? We want each electron to be positioned so that they're in the lowest energy arrangement possible, and the lowest energy arrangement possible means that we just add up. Now, this brings us to the Pauli exclusion principle. The Pauli exclusion principle says no 2 electrons in the same atom can have the same set of 4 quantum numbers. So some things to remember. The s subshell holds 1 orbital, 2 electrons max. The p subshell holds 3 orbitals, 6 electrons max. The d subshell holds 5 orbitals, 10 electron max. F holds 7, 14 electron max. So we're going to look at helium, lithium, beryllium, boron, and look at their electron configurations. And I'm going to draw some stuff for you. So I'm going to have to sit down the camera, and we're playing in my office, and draw some stuff. Okay? All right, now there's the drawing board. So that we got a pretty good look at it. How we doing? Okay. Not as good as that. Okay. How's that? All right. When we look at hydrogen, hydrogen has 1 electron. The lowest energy position is 1s. We're going to look at N, L, M sub L, and M sub S. Lowest energy position is always N equals 1, and it has the S subshell, which is L equals 0. That means M sub L is 0, and M sub S could be plus a half or minus a half. We usually go with plus a half first. So there's hydrogen. Make sure we can see that. Okay, if we go to helium with 2 electrons, N, L, M sub L, M sub S. I know that its first electron is going to be 1, 0, 0 plus a half, because that's what hydrogen's electron was. But helium has 2. Now the first shell has 1 orbital, and each orbital can hold 2 electrons. So the second electron is going to be 1, 0, 0 minus a half. Those 2 electrons are both in the first shell in the S subshell, but they have different spins. If we now move on to lithium with 3 electrons, N, L, M sub L, M sub S. I copy what I did for helium, 1, 0, 0 plus a half, 1, 0, 0 minus a half. Okay, so that's the first electron. There's the second. Now when we look at the third electron, the 1s orbital is filled. That means the first shell is filled. So I'm going to go to the second shell. Okay? The lowest energy in the second shell is 2s. S has an L value of 0, so it's going to be 2, 0, 0. We usually go with plus a half first. So our electrons in lithium are 1, 0, 0 plus a half, 1, 0, 0 minus a half, 2, 0, 0 plus a half. So you can see Aufbau at work here. 1, when I move from hydrogen to helium, you can see I just added 1 more electron. Helium to lithium, 1 more electron added. If I go to boron, I add another electron. And this should be the missing segment out of 3.1.